Okay, yeah, so shall we start? Okay, so welcome back. What we will continue is now we'll continue our discussion on the cryptography. So far in the sessions, what we have done, we have completed classical ciphers, right? We have completed classical ciphers, then symmetric ciphers, then asymmetric ciphers, right? We have given a detailed discussion on these various classical, symmetric, asymmetric ciphers. We understood how they work, right? Then, by doing these encryption algorithms, by implementing, what is that we were aimed to achieve? What is that we are trying to achieve? What is the security objective that we are trying to achieve? Confidentiality, right? So, we were trying to achieve confidentiality, right? Now, I have a different objective, right? The different objective is number one, how do I ensure integrity? Okay, how do I ensure integrity? Also, another objective is authentication. So, integrity, authentication, right? How do we ensure this? Now, in order to do this, we have separate another kind of ciphers called hash functions. Okay. So now we will discuss hash functions. Hash functions are also called as, number one, they are keyless ciphers. Okay, they are called keyless ciphers. Symmetric, how many keys we have used? Asymmetric, how many keys we have used? And keyless ciphers are the hashes. That means there is no key. Okay, there is no key. Here, the objective, the main objective is to have integrity. Our objective is not confidentiality. We are not aiming at confidentiality. And another thing, these ciphers, you need not decrypt. You cannot decrypt. You cannot decrypt. You cannot decrypt. Okay, so that means it is this way. It is this way. See, typically in an encryption process, what we do, can I get a small piece of paper, Anvarasu? Okay, let us see this. So, during the encryption process, what we do, we systematically encrypt the message to create the ciphertext. That means, if this is my message, in order to conceal that, what we have done, we have made some systematic foldings, right? So, one this side, imagine the encryption process says one this side, another one this side, right? And another one this side, and another one this side. So, these are all the steps during encryption process, right? So, you send this ciphertext, what the receiver do? Receiver systematically do the decryption process. What is the decryption process? Exactly reverse process, right? So, you unfold in the way that you have folded, right? You get the plain text back. Now, what is the hash function is doing? Hash function is also creating a ciphertext. Hash function is also creating the ciphertext. That means, when I say ciphertext, C is equal to, okay, the ciphertext C is equal to hash over plain text. Okay, C is equal to hash over the plain text. So, the H is my hash function. Had I written it as E, Generally what we do, C is equal to E of P comma K, E of P comma public key, whatever it is. Had I written E, I have written H. So what is H? H is a hash function. What this H is doing? H is actually doing, taking the plain text and it is going to compress the text. Okay. When I say compress the text, it is actually creating the digest. Now you see, is it systematically done in a way that, yes, it is actually systematically done to create the digest. But the point is it that decryptable? Is it that it is decryptable? No. So it is not for decryption. So what I got is called the digest. So this particular ciphertext, what I have got is not actually ciphertext, rather it is the message digest or signature. Okay. So what is the output of the hash? Output of the hash is the digest or the signature. Okay. So there are, like, you have looked at encryption algorithms, right? They are symmetric and asymmetric. The hashes have certain properties. It's not that you can take any function and call it as a hash function. Okay. So let us understand what are all those basic properties and all, right? So far whatever we have discussed is confidentiality, but we have not focused on integrity. So how do we do it? So in order to say that integrity of the document, integrity of the message is preserving, what is the way out is create the signature of the message, create the digest of the message, right? So how it happens? So take the message, the plain text, okay, apply the hash function H over the plain text. So what you get is the digest, message digest, right? So take this particular message digest, send it to the receiver. So all this happens at the sender side. What is that? Plain text message, creating the digest of the message happens at the sender side, and at the receiver side, what they do? Take the message and also the digest. Okay, so the message P and the digest both are taken. Then what they do? At the receiver, they calculate digest over the plain text. What they do? They calculate digest over the plain text. Once they calculate the digest over the plain text, what they do? They check whatever the received digest, whatever the calculated digest, both are same or not. Okay. If both are same, what does it mean? Integrity of the message is preserving. If both are different, the integrity of the message is not preserving. Integrity of the message is lost. That is what is the conclusion, right? So what you do is sender takes the message, calculate digest of the message using how they calculate the digest? Using hash function. Then what he will do? Send the original message and digest to receiver. Receiver, what is receiver will do? Receiver calculates again digest over plain text, which is received plain text, okay, if received digest and calculated digest are same, then message integrity has preserved. Otherwise what? Integrity of the message is lost. Okay, so that is what is the steps, right? So pictorially also you can see when the message is being sent, okay, the sender calculates the digest, send the message and digest to the receiver, receiver again calculate the digest over the received message, check the received digest and calculated digest. If both are same, then fine, otherwise conclude that integrity of the message is lost. Now, the point is, when we say the hash functions, what are the things so far we have said? Hash functions create message digest, okay, and hash functions are keyed or keyless? They are keyless ciphers, okay. Their purpose is to decrypt or not to decrypt. So the purpose is not to decrypt, it is to verify. Yesterday sessions there were a discussion about verification. So how do you verify? You need to have a digest, okay. Now the point is, how do I do it? And it is also called as compression function. It is also called as compression function. Why? You are creating digest of the original message. If you have noticed, what is my original document? When I have crunched it, this is a very small digest. What is my original message? My entire page, right? So that means I have taken a lengthy message, converted to a small digest. So what I did, it's a fact of compression. So that's why you will call that as a compression function also. So now, is it that I can use any compression function? There are certain properties that it should satisfy, okay. Let us see what are the properties. Number one, my hash function can take any length message. I have just shown with one page, one document, it can take any length message, okay. There is no restriction, but the output is fixed length, okay. So when I say digest, if I say that my digest should be 512 bit, irrespective of the length of the message, digest should be always fixed. So fixed length, okay. And first of all, such function should be computationally efficient, right? I should be able to compute the digest. Then, whatever the output I get, it is sensitive to all input bits, okay. It should exhibit strong avalanche effect. By the way, where we have discussed avalanche effect? While talking about DES, we have introduced avalanche effect. Any single bit change or a minor change in the plain text should result in major change in the corresponding ciphertext, right? So when it will happen? If it happens only if output is sensitive to all input bits, okay. So there is a diagrammatic illustration. You see here the message. Remember, the message digest is of fixed length. You see, whatever the input I am giving, input is variable length, but you are getting fixed length message digest, irrespective of size of the message. Then even a minor change, you see here there is a minor change in the text. You see the difference that the message digest that it has produced, right? So these are all the properties of the hashes. And there are three conditions that the hashes should exhibit. Okay. What are the properties we have seen? The three properties that what we have seen so far is input can be of any length, output is fixed length, output is sensitive to all input bits, and the algorithm or the hash function is computationally should be efficient. What are the requirements of the hash functions? There are three requirements. It says pre-image resistance, second pre-image resistance or second collision resistance. The second pre-image resistance is also called as weak collision resistance. The final one is called strong collision resistance. What is that? These are the three conditions. What are these three conditions? The first one says pre-image resistance. It's also one-way property. Means the hash functions are decryptable or should not be decryptable. So that means if I have a message, I should be able to create the hash, but if they have the hash, I should not get back my plain text. So given x, calculating h of x is computationally should be feasible, but having h of x, getting x should not be feasible. That is called pre-image resistance. Okay, pre-image resistance. But this is the condition. Ideally, any hash function should satisfy this particular property, right? Then all hash functions what we have, they satisfy this pre-image resistance. Having a plain text, it is possible to create the digest, but having the digest, one should not be able to get the plain text. There are two more interesting properties, conditions. Second, pre-image resistance or weak collision resistance. You need to understand what is meant by collision. See, what is that we are doing in the case of hashes? We take a large plain text, trying to map it to small space, right? My input length is large, my output space is small, right? When I am mapping like that, there are chances that two plain texts getting same digest. Okay, it is this way. Now take an example. How many days are there in the calendar year? 365. We have a paradox called birthday paradox. Now imagine I have, say, 100 people. I have 100 people and I have 365 birthdays. When I try to map their birthdays of these 100 people to 365 days, is there any chance that I get two people having the same birthday? There are chances, but the probability could be even 0, right? It need not be always 1. But imagine I have 500 people. Imagine I have 500 people. Then what is the probability? Certainly, right? Certainly I will have some people having birthday on the same day. Why it is happening? Why it is happening? Because the number of people are more, number of days is less. Now what we are talking in the hash functions? We are saying variable length input, fixed length output. So obviously collisions will happen, right? Obviously collisions will happen, right? What is the ideal hash requirement is that one should not get the collisions. Okay, that's the ideal condition. But would it happen like that in a practical scenario? No. The reason is You are taking a large space of input, trying to map it to a fixed length. So like as I said, 500 people is your input, 365 days is your output, that is fixed. That is fixed. Obviously, you will have a collision. Now, as per this, based on this particular premise, the requirements of the hashes says, the weak collision resistance says, if I have one particular message x1, and its corresponding hash, I have x1 and its corresponding hash. What is corresponding hash? H of x1. Okay, I have the information about a message x1 and its corresponding h of x1. What is the weak collision resistance says? When I have these two, I should not get another message called x2 having the same hash. That is called weak collision resistance. Okay, I should not get another message. With same hash, that is called weak collision. There is the third requirement. What is the third requirement says? Third requirement says I should not have two messages having same hash. I should not have two messages having the same hash. It looks both are same, but it is this. What is the weak collision says? There is one person whose birthday falls on, say, December 8th. Is there anyone whose birthday is falling on December 8th? This is the problem. That is weak collision. What is the strong collision says? Hey, among you who are having birthday on December 8th, are you able to identify the difference in the problem? I have one information trying to check who is having the birthday on December 8th. Now, what is the second problem? I don't know. Look, I picked him. What is your birthday? Okay. What is your birthday? Your birthday, your birthday. Then I checked. Then no. What is your birthday? Then again check. Right? So, that is strong resistance, strong collision resistance. The first one is the weak collision resistance. If you have weak collision resistance, that doesn't guarantee the strong collision, but if you have strong collision resistance, it guarantees the weak collision. Okay. So, these are the three requirements for the hash functions. Are you able to follow? Right. What are the various hashes we have? There are several hash functions we have. Now, what we are following is the SHA-512 secure hash algorithm. SHA-512. There are other algorithms. Now, if you notice, what is the input? The input is 1024. Sir, you said variable length input, but the input size it is fixed as 1024. What does it mean? It means you can take any length input, but what is this 1024 says? Block size is 1024. So that means typically hash of SHA algorithm works as a block cipher, right? So take the plain text, divided it into multiple blocks, block size is 1024. What is the digest size? Digest size is 512 bit. Okay. And remember, in order to do this digest creation, it runs in multiple rounds of operations. Okay, like you have seen the multiple rounds, right? In the case of DES, we have seen, in the case of AES, we have seen multiple rounds. In a similar way, there are certain rounds of operations, 80 rounds. Okay, there are no collisions. So the point is this: we all know that when you are mapping from a large space to the smaller space, hashes will have the collisions. But then, what is that, on what basis we are using those hash functions? The reason is that if we know that there are collisions, but are we able to find it? Knowing is one thing, finding is another thing. So there would be collisions, but we don't know what are those collisions. Okay. So this is how the SHA-512 algorithm works. Look at this. Take the plain text message, divide into 1024-bit blocks, and each block undergoes the compression function. So this is called a hash function, typical hash function. Since it is doing the compression activity, it is called compression function. Output of is 512-bit, and that output goes as input to the next block. By the way, this way of processing is what type of mode? Which mode of operation? CBC mode, right? Okay. The reason is you take the cipher, submit it as an input to the next block, and take the output, submit it as a next loop. So the point is, after processing the final block, whatever the 512-bit that what you get is the overall digest for the entire message. So this is my, imagine this is my entire message. The final 512-bit what I get is the digest of my overall message, right? So this is how it proceeds. Are you able to follow? Okay. I am not going to deal with this hash function per se, the SHA-512. It is illustrated in the book. So please go back and then check how actually the SHA-512 algorithm it works. So you can see the multiple rounds of, I said 80 rounds. So round 0 to round 80, round 79, that means 80 rounds of operation, how it goes. Okay. And obviously you have the message digest is getting created at the end, but message schedule, you take the message is of size 1024-bit, and you are operating for how many rounds? 80 rounds. So your message is 1024-bit, your cipher that is it is produced is 512-bit. So how actually your 1024-bit message is going to 80 rounds of operations? That all is about message scheduling algorithm. Remember, we saw one scheduling algorithm in the case of DES and AES. What is that? Key scheduling algorithm. Here we are talking about message scheduling algorithm, right? So please go back and check. Next, we also have message authentication, okay, called MAC codes. What we have achieved with hash? With hash, hash functions helps us to check the integrity, to verify, right? Hash functions help us to check the integrity of the message. Now the question is, who sent this message? Authentication, right? How to achieve authentication? So for that purpose, we have set of codes called message authentication codes, called MAC codes. So to verify that the received message is coming from a particular source, and also it is not altered, that means integrity is preserving. Okay. So how do we do that? In order to do that, Alice is sending a message to Bob. What Alice did? Took the message M, and then see here, she submitted that message to the hash. Okay, she submitted the message to the hash, but what is that hash is also taking the input? What is the diagram says? What is the diagram says? It is also taking, no. See the input. Hash is taking the input, which is a key. what we said previously, hash is a keyless cipher. Now you see what you are doing. In the case of Mac, you are giving key to the hash. Now you are submitting key to the hash. Message and key are submitted to the hash, right? So when you submit the message and key to the hash, what you produce is the MAC code. So that means keyed hash is MAC. So MAC is nothing but keyed hash. Okay, my hash is not taking key. How can I submit the key to the hash? How can I submit keys to the hash? You take the key also as one of the block. You take key also as one of the block. What is my plain text block in the case of SHA-512? 1024, right? So what I do, I take my key, submit it as a block to the hash function along with my plain text. So that's how you get the keyed hash. So you produce the MAC. So what you do, you take the message and also you take the MAC code, send them in the insecure channels such as internet. What the receiver would do? Receiver takes the message. Receiver get both message plus MAC code. Then what the receiver is doing? Calculate MAC over message. How he calculates? Submit the key and the message to the hash function. Which key here? Which key? When I say key, which key it is? Symmetric or asymmetric? So symmetric. So the key is symmetric key, right? So what he gets is the MAC code. Finally check whether the received MAC and calculated MAC both are same or not. Then once he checks if both are same, what is the conclusion? Number one, what is the conclusion? Integrity is not lost. Integrity is not lost. Then what is the other conclusion? Yeah, what is that conclusion? This message is sent by Alice. Why these conclusions have come? Because you are able to get the same MAC code as we have received, so integrity is preserving, number one. Number two, for creating the MAC code, the same key is used, right? And who has that key? The key is with Alice. So Alice has sent the message, right? So there are two types of creating MAC functions called hash-based MAC codes, cipher-based MAC codes. Okay, you can go back and then check how you can create hash-based MACs, cipher-based MACs, right? Hash-based MAC, this is cipher-based MAC. So we have seen that hashes have helped us to check the integrity. MAC codes have also helped us to check the authentication, right? So if you want to closely observe the so far encryption algorithms working, number one, you see here what Bob has done. Imagine Bob to Alice. Okay. to have the communication between Bob and Alice, what actually Bob did was created the symmetric key. Okay, that symmetric key is encrypted with the help of Alice public key. With the help of Alice public key, because Alice has a key pair PUA, PRA, Bob has key pair PUB, PRB. So Bob has encrypted the symmetric key with the help of Alice public key, and then this particular encrypted symmetric key is shared with Alice. So Alice decrypts that with her private key, then gets the symmetric key. And once this key establishment is done, what all next happens? This communication between both of them would be symmetric communication, symmetric encrypted communication. Right? You must have also listened in the few days about two things: digital certificates and digital signatures. What are the difference between certificates and signatures? What are the difference? Okay. Okay. Signature. You need to understand the difference between both these entities, number one. Number two, where they are used, right? Let us go back to this key exchange problem of this one. We said symmetric key is created by Bob and encrypted using the help of Alice public key. Now the question is, how Bob knows public key of Alice? Sir, it is public key of Alice. It is public. Correct. When it is public, anybody can use it and anybody can tamper it. Anybody can tamper it, and what is the guarantee that whatever I got the key as a public key of Alice is actually the public key of Alice? The integrity of that is not tampered. How do we know that? So that means we need some mechanism. We need some mechanism to know for sure whatever the public key I have received is actually the public key of that particular person. How do I know? So certificates are issued to authenticate public keys. So the digital certificate purpose is to authenticate the public keys. Hey, look, this is the public key of Alice. And who says that? There should be a certificate authority who says that, issued by certificate authority. There are several commercial certificate authority providers to provide security certificates, right? When I say certificate, what is essentially is that it is about the public key. Okay, so see the scenario. Alice wants to talk to Bob. So Alice wants to know what is the public key of Bob. What Alice will do? Alice will ask the certificate authority. Alice will ask the certificate authority, first of all, please give me a certificate. Similarly, Bob also will ask the certificate authority, please give me a certificate. When they ask what they communicate, they say that to the certificate authority, hey, look, This is my public key. Can you issue a certificate? Can you issue a certificate? So look at this. Certificate authority responds back to the requester with certificate. Okay. Look at that certificate format. First of all, is it an encrypted piece? Is it an encrypted piece? That certificate is an encrypted piece or not? It is an encrypted piece. How it is encrypted? It is encrypted with the help of private key of authority, right? So, a certificate is encrypted with so that means I ask the authority, please give me a certificate, and this is my public key. What the authority would do? Authority would encrypt my public key with authority's private key. So when something is encrypted with the private key, how it could be verified? It could be verified with public key of, yes. So certificate is encrypted and issued by authority. Verification of the certificate happens with public key of authority. Anybody can verify it because anyone knows the public key of the certificate authority, they can verify the certificate, right? So in this scenario, if you notice, A got her certificate, B got her certificate. Then what they do? They exchange the certificates. When A sends the certificate to Bob, can Bob verify the certificate? Verify with public key of authority. Same happens here also. A would verify the B certificate, B would verify the A certificate. Certificate contains what? Essentially the public key of the other entity. And the other day, in the sessions you have understood that there are certain certificate formats. X.509 is a certificate format. It is not that the certificate contains only the public key, there are a lot more information depending on the format. X.509 is the typical format, it contains so many other informations. So the digital certificates are essentially meant for knowing in an authenticated manner what is the public key of other entity, right? Then, what is the next one? Digital signatures, right? Digital signatures. Okay, first of all, why we sign on the document? Imagine there is a circular you receive, you look for somebody has signed on it or not. Not only the circular or any document for that matter. Why? Number one, when I am issuing a mail or a letter, when I write a letter, I will sign on it. That means I am saying that, look, this letter is written by me and I know the content of the message and I am authenticating it. How do I say that? By signing. Okay. In a similar manner, you have digital signatures in the real world, in the digital world. Okay. So the purpose of the digital signatures, if you notice, generally message authentication protects two parties who exchange the messages. However, it does not protect the two parties against each other. What is it meant by that? So far, when Alice and Bob are interacting, there is someone called Eve who is either listening to the conversation or who is either tampering the conversation, right? That's what we were assuming. Now, the question is this. Alice is sending something to Bob and later says that, no, I have not sent this message, right? So that means the threat is between This too itself. So the point is that there are several forms of disputes can happen when there are transactions, there are communications between entities, right? So what is a digital signature? Signature is an authentication technique which also includes a measure to counter repudiation. I think in the very beginning we talked about confidentiality, availability, integrity, authentication, and I said non-repudiation, right? So what is the digital signature is doing? Countering the repudiation. What is that countering the repudiation? Message is sent and saying that no, I have not sent the message. So when I sign the document, it is that I am sending, this is my message, right? So how do we do that? So any digital signature actually verifies the other who created that particular message. The signatures, digital signatures helps to verify who created the message, the date and time of this message, and also it authenticates the contents of the message. That means when I am creating a signature, the signature should be based on contents of the message. Look at the normal signatures. Whatever is the content, your signature would be same, right? On a physical document, digital signature cannot be the same. When you create a message, your digital signature for that particular message, it is unique. When you create a second message, for that second message, your digital signature would be different. For your third message, your digital signature would be different. So for every message, your digital signature varies, unlike your physical environment. So there are various differences between the physical signatures and the digital signatures which you should actually understand, right? Because you are creating the digital signature even to authenticate the contents of the message. Okay, so that means your signature is based on the content. Okay, so that you should remember. Okay, so there are several, several properties that you should learn. Now, if you notice how the signature happens, now you see here, Alice is creating as a message. How the Alice is signing? There is a signature generation algorithm using which Alice actually signs the message. So this is called signature generation algorithm. Okay, and once the signature is generated, it would be encrypted with the whose public key it is? Whose public key? Bob. Who is Bob? Receiver. Encrypting with the receiver's public key ensure what? Confidentiality, right? So you send it. And decryption is happening with the Bob's private key, so you are achieving confidentiality. Now what is this here? Signature verification. How do you verify the signature? Signature is verified with the help of Alice public key. Now, how Bob knows what is the public key of Alice? Using? Okay. So there are several digital signature algorithms using RSA based, Elgamal based, right? There is NIST designed their own, the digital signature algorithm called DSA algorithm. There are various algorithms. So now you understood that the purpose of digital signatures is to provide what? Authentication and also ensure non-repudiation. Are you able to follow? How it is done? Signed with, message is signed with private key of signer, verified with public key of signer. Okay. There are varieties of digital signatures, which is called direct digital signature, which is what we have discussed. Okay, direct digital signature. Then there is another digital signature called arbitrated digital signature. What is the arbitrated digital signature? There are two people who are into the transaction, Alice and Bob. Okay, Alice said, okay, look, I want to send a message to Bob, and that message, Alice is not signing. Alice is taking it to an arbiter, third party, asking the third party, because these two people, they are non-trustable. They don't trust each other. Non-trusted communicating parties. So far we said Alice is talking to Bob, Bob is talking to Alice. So far we didn't bring the role of trust here in between. So now that these two guys are not trusting each other. So Alice created a message, asked the third party to sign the message. So arbitrated digital signature. There is one more digital signature called blind digital signature. If you see here, the purpose is, say take an example, I want to vote. Okay. So I go to the election authority asking for the authentication and saying that I want to make a blind vote. So then authority checks my credentials and then sign on the blind vote, so that he says that yes, he's the guy who can cast the vote. Now you see here, it is called blind digital signature in the sense that what is that actual vote? What I am casting is blinded to the election authority and to the casting of the vote. So finally, verification happens only at the center. The verification happens with the voting center. Okay. So this is a blind digital signature. So there are digital signatures based on the needs. Okay. So one should understand the difference between your, the digital certificates, the digital signatures. What is the use? How do you create? And for what purpose? Is that clear? So these are the about various aspects of the digital signatures, digital certificates, and cryptographic primitives. So this is very broad understanding we have provided in terms of cryptography, starting from classical ciphers, modern ciphers, then the way these ciphers are getting implemented, their classifications, applications, right, starting from symmetric, asymmetric, keyless, then authentication codes, certificates and signatures. The other day, in the network security, you have seen the digital certificates, you have seen the signatures creation, right? You have seen the digital certificates that are issued by the Microsoft that are there in your system. They follow a certain particular format, as I said, so all that, basis is this. Okay. So before we conclude the session, I also would like to throw some light about, the current hot topic, which we call it as a impact of the quantum computing on the cryptography. Why this is happening, how it is happening. Okay. So essentially, in the so far covered cryptographic algorithms, we have seen public key cryptography algorithms. They are rooted on complexity of certain mathematical problems. If you especially notice the the public key cryptography, it is based on finding the prime factors. That means it is simple. If you notice, imagine I have two numbers, P1, P2, which are prime numbers. I can multiply them and get an n. So this is fairly simple process. Okay. But the issue is the reverse. What is the reverse? If I have n, getting this P1, P2 is the complex. That is the problem, right? That is the fundamental problem on which your public key cryptography RSA algorithm is based on. Okay. So there are no mathematical shortcuts to address these problems. Now what is happening? In the case of quantum computers, in 1994, there was an algorithm from Peter Shor, who has brought in an algorithm called Shor algorithm, okay, which in fact is trying to solve that particular mathematical problem on which RSA is based upon. Now, what is this quantum phenomena or quantum computing? Now, we all have heard or read that quantum computing is trying to provide massive computing power. First of all, how do we achieve higher computational power? In general, for classical computers, either we can increase the computational power by making the operation faster. That means you can increase the CPU clock frequency, or you can also increase the number of operations completed using in particular during each clock cycle. Okay. So these are the ways your classical computers achieve higher computational power. Okay. But quantum computers achieves high computational power in a different means with the help of quantum computing or quantum physics. We will not go to those aspects, but we will see what are the basics of these quantum aspects. We all know that what is the fundamental unit of computer? A bit. A bit which holds two values, either 1 or 0. In the case of quantum computer, it is called qubit. Okay. We will understand the quantum computer in three ways. Okay. Number one, so we will understand quantum computers in three ways. Number one, how information is represented. Number one. Number two, how information is processed. The third one is, how do you handle the results? Okay. Let us see how these three things are happening in the quantum computer. Okay. If you notice, in classical computers, we take bits, they represent the information either 0 or 1, right? In the case of quantum, what we call these bits as qubits. Okay. What they do, they represent the information not just as 0, 1, but both 0 and 1, and also the information can be even negative values. Okay. It is called, this phenomenon is called superposition. Just to give you a brief, this one. So if you see the coin, typically you have a head and tail, right? So when you throw it, either it would be head or tail. At any point of time, like bit will have 1 or 0. Now, the quantum computer, the qubit actually represents. So now if I imagine, if I spin this coin, what happens? Coin is in the spinning state, right? So coin is in the spinning state. That means when I spin the coin, so you can imagine that the coin is in the spinning state. What happens? It rotates, right? It oscillates in different angles, 0, 1, or head, tail. It moves. Some, head, tail, head, and with different angles. Now you can think that a qubit is a kind of a spinning particle oscillating between 1 and 0. So beauty is that so far there are, till a decade back, there are no ways physically how do you build such type of bits which can spin between these two states. Now people are able to realize with the with the various technologies like adiabatic, then quantum annealing, gate based, people are able to mimic these kind of qubits which would be in the states of not just 0, 1, but between 0, 1 and 0 and 1 together. Okay, so such type of state is called a superposition state. Okay, so you need to understand that word called superposition. What is meant by superposition? Superposition means a quantum bit What is quantum bit? Qubit is in multiple state. Whereas in the case of classical, what happens? You have only one, either 0 or 1, right? And another important property of this, the qubits is that, in the case of a classical bits, this is one bit, okay? Imagine you have one more coin, it is another bit. But these in the case of quantum computer, these qubits are all interlinked, okay? So they work together. So that means one qubit affects another qubit affects another qubit. So this type of phenomenon is called entanglement, okay? Entanglement. So superposition, entanglement, right? So if you notice, as I said, you have 0 or 1 possible states. In the case of classical computers, all classical algorithms, the computers that what we work, the algorithms that the classical computers process, they are all deterministic algorithms. That means what is meant by deterministic? When I take an algorithm, when I submit an input, I get an output. When I repeat it, whether I get a different output, I repeat another time. Same input, same algorithm, I repeat n times. Will I get the different outputs or same output? In the case of quantum, it goes this way. Number one, it is not that you have only 2 states, you have infinite states. The reason is, when you spin the coin, you would have noticed that it is in various positions, right? Infinite positions at different angles. When you spin it, it is at different angles it spins, right? So infinite positions, number one. Number two, output is probabilistic. So that means when you implement a quantum algorithm, output is not deterministic. So sometimes people get carried away that future quantum computers will replace classical computers. So these desktops will be replaced with quantum computers. No, certainly not. The reason is your output is, but real world all our problems are what? You are supposed to be deterministic, right? You can't run a algorithm giving you input, once it will give you one output, another time when you run the algorithm it will give a different output. You can't go with such type of algorithms. So classical are deterministic, quantums are probabilistic in nature. Sir, when it is probabilistic, how do you decide what is the output? You need to handle it, you need to know output, right? How do you handle it? So there is a different ball game. So we will discuss that also in time permits. So how do you process the information? When you are processing the information, so you handle it. In the case of classical bits, typically a classical computers, what happens? Process the bits in a sequential manner, right? Sequential. I'm not talking about the parallel computers, parallel execution of the algorithms, no. Typical classical computers goes in sequential. In the case of quantum computing, what happens? The processing, since you have the superpositioned qubits, which are entangled together, that means a superposition the qubits which are entangled together, multiple such type of qubits, which will provide you a massive computing power, and hence you will be able to solve certain problems very quickly. Okay. How do you interpret the results? As I said, classical systems provide deterministic answers, quantum computing systems provide probabilistic answers, right? So these are the things that one should remember. So just to visualize, in the case of classical computer, if you take a bit, 2 bits if you take, what are the possible states? 0, 0, 0, 1, 1, 0, 1, 1 at any given point of time. You take a AND gate, how do you 0, 0 you get? 0. 0, 1, 0. So you give the input, you get the output for the given state. Now in the case of a 2-qubit, you get 4 possible basic states all at a time. All states are possible at a time. Okay. Similarly, if it is 3 qubits, now think of the number of qubits. Okay. What we said, because of superposition, that is one aspect. Another one is entanglement. What is meant by entanglement? Bits interacting, influencing each other. And when they are interacting and influencing each other, that means they are exposed to the real environment, and hence what happens? You induce noise, they expose it to the noise. Okay. So far, people are unable to handle the noise among the qubits, and that is the reason why, what people are talking is NISQ, noisy intermediate state quantum computers. What people are talking. Okay. What so far we have, quantum computers are all noise based. Okay. Not noise free. Okay. So there is a quick comparison between the classical computers and as well as quantum computers. Please look at this particular reference, the past, present, future of scalable computing technologies. Okay. So there is a very good article in that. There is a quick reference difference between the classical and as well as quantum. Now, yes, we have gave a very broad overview of quantum. Now, how it is influencing this cryptography? If you notice, we have discussed AES, which is a symmetric key encryption. If quantum computer comes into picture, you require larger key sizes of AES. That's all. You need not go for replacementing of the AES. Again, in the case of SHA, that means hash functions, again, you need to go for larger outputs. So when you have seen variable length output to the fixed length outputs of hash algorithms, you should go for a much larger this one. But in the case of public key cryptography algorithms, they would be no longer secure because of the quantum computer able to solve what are the problems? What are the problems that these particular algorithms are based on? Discrete logarithm problem on which your Diffie-Hellman key exchange is working, prime factorization problem on which your RSA is working, right? What is the algorithm that is posing the threat from quantum computer is the SHAR algorithm. I don't deal the algorithm now. What it do is, the SHAR algorithm, you can go to the online, find various resources, but SHAR algorithm has managed map the factorization problem to period estimation problem. Period estimation problem. I'll just give you an example for what is period estimation problem, then you will be able to understand. Because generally, when you go to the various resources, they don't provide this. So take an example. Imagine I have a function. What is the function? Function is in this form. Imagine that there is a function which is in this form. Are you able to map it to an algorithm called RSA? What is that you do in the case of RSA? C is equal to, right? So now what happen is, imagine I have n is equal to 15, k is equal to 7. Okay, n is equal to 15, k is equal to 7. What I am doing is, I am trying to find this x value. Okay, so for in the case of in the case of RSA, it is C is equal to m power e mod n. Now see here, look at this particular case. I am trying this to solve, to x is equal to 0, so on. Okay, what happens when I give x value from ranging from 0 and so on? What happens? So I have, when x is equal to 0, 7 power 0 mod n. What is mod n? 15. Then and goes on, right? And goes on. Now if you notice, in this series, you have 1, you have 7, and when you proceed further, 4, 13, and then what happens? 1, 7, and goes. That means what? You see these values gets repeated. The period estimation problem is to find the period where the values are getting repeated. Okay, this is called period estimation problem. Now, what the SHAR has done was, SHAR has mapped the prime factorization problem to the period estimation problem. Okay, so you need to understand how this period estimation problem is solving the prime factorization problem, number one. Number two, he also has brought out a quantum circuit for that. Okay, we all know that you have bits, gates, circuits on which the classical computers are built. Similarly, you have qubits, quantum gates, and quantum circuits. So a circuit was built to calculate a SHAR algorithm. Okay, and because of that, what happened is, you are finding the prime factors was able to solve, that was able to be solved. Okay, and with a significant speed up. Okay, there is one more algorithm in quantum computers called Grover algorithm. These are the two algorithms that pose the threat to the cryptography. What is the Grover algorithm? Unlike SHAR algorithm, which is solving the prime factorization problem, Grover algorithm is helping us to perform the search operations. In the case of hash functions, I gave one search problem. What is that? What is that? Hash function requirements. Trying to find the collisions. We know that for any hash functions, collisions do exist. But why we are able to depend on the hash functions? Because you can't find them. Okay, but the search algorithm from the quantum literature called Grover algorithm will help the people to find the collisions. That's where these two algorithms pose threat. Okay, so if you notice the timeline of quantum computers, we are somewhere here, from today to the next 10 to 15 years time span, we call post quantum cryptography. So there are two terms which you should understand. People talking. Number one, post quantum cryptography, quantum cryptography. There is a difference between both. Post quantum is all about how to make quantum resistant algorithms. That means I have the SHAR algorithm breaking my public key. How do I resist it? I have the Grover algorithm which is going to impact my hashes and symmetrics. How do I resist it? What are the algorithms with which I can resist the quantum attacks? Okay. How do I resist quantum computers' influence? What is quantum cryptography? Quantum cryptography is about how do I leverage the quantum computing principles? To provide security. Okay. The most popular algorithm of quantum cryptography is BB84 algorithm. The purpose of BB84 algorithm is to provide key exchange. For key exchange purpose, what we did, imagine you want to exchange the symmetric keys. How we did? We used RSA or asymmetric key cryptography. But we said asymmetric key cryptography is in danger because of quantum. So that means without using asymmetric key cryptography and using the quantum computing principles, BB84 protocol is able to exchange the keys between the communicating parties. Once the keys are exchanged, communication happens with the symmetric key algorithm, right? So for BB84, in order to implement BB84 algorithm, what is needed? You need quantum computers. So quantum computers, if you have, then quantum cryptography is possible. That is the reason why if you see the slide, if you down the line of next 10 to 15 years, you may have quantum cryptography. But now what people are talking is post-quantum cryptography. Okay, PQC, then quantum key distribution, that is the quantum cryptography. Okay, so I think you must have got a very broad overview of quantum impact on the cryptography and what is quantum cryptography, what is post-quantum cryptography, right? Is that fine? And if you are really interested about the post-quantum cryptography, there are 4 branches. One is called hash-based signatures. By the way, have we discussed hashes? Today we discussed hashes. So hash-based signatures are one of the branch of post-quantum cryptography. Then you have multivariate cryptography, wherein which, depending upon solving the multivariate equations, you have multivariate cryptography. Then 2 more interesting aspects called code-based cryptography, wherein which, while encryption, you induce an error into the code, and then at the receiver, you remove the code, you remove the noise. An attacker will not be able to remove the noise. That is what is the phenomenon of code-based security, code-based cryptography. Then you have lattice-based cryptography, which is taking the help of lattices. That means, any objects, if you notice in a real world, they form certain geometrical shapes. Inspiring the properties of geometric shapes, we have the lattice-based cryptography. So these are the various 4 forms of post-quantum cryptography that what we have. Under each branch, various algorithms are there. And these algorithms are now under verification of NIST. Okay. So NIST is verifying various algorithms under each branch, and they are trying to standardize it. Okay. So with this, we will conclude the cryptography sessions. We gave extensive coverage of cryptography fundamentals, classical ciphers, then symmetric ciphers, asymmetric ciphers, keyless ciphers, and various modes of operation. Then we have talked about authentication codes, digital certificate and signatures. And all these things are helping us to achieve confidentiality, integrity, authentication, and non-repudiation. These are the security services. Then we briefly touched about the quantum computers' influence on cryptography, how they are getting impact on various cryptographic algorithms on the symmetric side and asymmetric side. Okay, fine.